Hello and welcome to this electrical principles training video. In this video we're going to consider researching what happens to the neutral current in a three-phase system. Now in a previous video we saw that if you have what we call a balanced load on a three-phase system, that means the same amount of current in each one of the conductors, then there is zero current in the neutral. And in fact we saw that you don't even need a neutral conductor in order for that circuit to continue operating, because there's literally nothing flowing through it. However, what we're going to explore in this video is what happens when you've got an imbalanced three-phase load. Now again, imbalanced means that you have different amounts of current inside each conductor. So we're going to set up our test rig with an imbalanced load. We're going to measure the currents in L1, L2, L3, have a look at the current in the neutral, and then we're going to have a think about how we get from that imbalanced current to our neutral current and how we can calculate it. Now there's many different ways that you can calculate neutral current. The way I'm going to show you first is the way that I prefer, because I think it helps you to actually visualize what's happening with the currents as they meet in the neutral, and also gives us a really accurate value for our neutral current and what it should be. We'll then explore some alternative methods of calculating the neutral current, all of which are perfectly valid and suitable, and we'll see which one you prefer to use. However, it's very important that when you get into your exam, you actually have a look at the question very carefully and see if it asks you to use a specific method, and if it does, you must use that method. So we'll have a look at a range. You can pick the one you like the most. We won't feature them all in this video, it will be a series of videos, so I think we get the rig set up and we do our testing. So in order to see what happens to our neutral current when we've got an imbalanced three-phase load, we've connected up our test rig in the following way. Over here in L1, I've connected up a 1 kilowatt load. And then over here, we've got two 2 kilowatt loads, and they're connected into L2. Now obviously we would never dream of connecting a 4 kilowatt load into a plug top such as this, because it could overload the plug top and lead to fire and overheating and other bad things like that. However, here we're working under controlled conditions and the heaters are only going to be on for a very brief period of time. So please don't ever think about connecting up a 4 kilowatt load on a single plug top, it's dangerous. And then over here, we've got our third load, we've got a 2 kilowatt load, and that is connected into L3. So you can see there that we've got three different size loads connected to L1, L2 and L3, which means that we're going to have different levels of current flowing through L1, L2 and L3. And that's what we mean by an unbalanced three-phase load. Different currents inside those conductors. So we'll power the heaters up, we'll measure the currents in L1, L2 and L3, and then we'll measure the current in the neutral, and then try and figure out why the neutral current might not be quite what we're expecting it to be. So we've got our load set up and connected. What we're going to do now is we're going to bring the camera in so we can see the readings really clearly as they're being taken from our rig here. So remember, we've got a 1 kilowatt load, a 4 kilowatt load and a 2 kilowatt load, and we're going to see what the currents are in L1, L2, L3 and all importantly inside the neutral. So since we started making this video, monsoon season has started here in Corby, and in this tin shed that we're working in, it's very loud on the roof, so hopefully that won't affect the audio too badly. So we've got our rig set up here. We've got a 1 kilowatt load connected through L1, we've got a 4 kilowatt load connected through L2, and we've got a 2 kilowatt load connected through L3. We're going to measure the currents in each of the conductors, and then we're going to see what the combined return neutral current is. So I've got my clamp meter set to measure current, so I'm going to power up the system and measure the current. So in L1, that's drawing 4.1 amperes. L2, that is drawing 16.1 amperes. And in L3, we're drawing 8.1 amperes. So we can see from that they're about the values we would expect based on the power that we're drawing and the voltage that we've got connected up. So those are our current values in L1, L2 and L3. Now what we'll do is we'll measure the current in the neutral. What does your intuition suggest that it might be? Well, let's measure it and have a look. So all that returning current flowing back through the neutral comes to 10.2 amperes. So we can see there that There's no kind of instant, obvious, clear relationship between those three currents that are flowing through L1, L2 and L3 and then back through the neutral again. So what we're going to do now is we're going to draw out exactly what's happening inside this three-phase system, and then we're going to figure out how those three currents flowing to L1, L2 and L3, how they actually relate to the neutral current. Let's go and do that now. So we recorded the three different currents that were flowing through L1, L2 and L3, and then following that we took the neutral current also. So we'll just make a little note of what those values were in the top corner here. So we had L1, we were drawing 4.1 amperes. L2, we were drawing 16.1 amperes. And L3, we were drawing 8.1 amperes. And then in the neutral, when we measured that neutral current, we found that we had 10.2 amperes. Now the goal of what we're about to do now is to try and reconcile these values. In other words, figure out how we can get from these three currents to this current right here. So how is it that when these three currents combine in the neutral, it comes out at this value of 10.2? What's the relationship between those? Well, there's a number of ways that we can figure this out, and the way that I'm about to show you is what I think is the best way of doing this for a couple of reasons. Number one, it gives you a visual representation of how the currents are behaving, and I think that's very important. And it's also the most accurate way of using a visual representation to give you the value that you're reading. Let me explain what I mean by that. There are some other mathematical methods which might be a little bit easier to remember and easier to process, and we'll cover that in a future video. There are other graphical methods that we can use in order to represent what's going on inside our three-phase system. However, those graphical methods are sometimes a little bit inaccurate because we're drawing them by hand and it can lead to some inaccuracies. So this method features the best of all those worlds. We're going to show you all the methods that I'm aware of on this series of videos in a future video, but for now we're going to have a look at this particular one. So the first thing we need to do is to draw what the currents look like in this three-phase system. So let's do that now. Now, I'm going to draw to scale what's happening with the currents inside this three-phase system. Now, I don't actually need to draw this to scale for this method. You can actually just do this with a rough sketch just to kind of help you visualize what's going on with certain of the values. However, I'm going to draw this one to scale so that you can sort of understand visually what's happening with these values. So first of all, I'm going to draw a line that represents my L1 current. So I'm going to allow 1 centimetre on my drawing will be equal to 1 ampere. So I'm going to draw a line starting here that will be 4.1 centimetres long. So 4.1 centimetres long. And I'm going to draw it pointing straight up like that. So I'm going to draw an arrow. There's my L1 value, and that line is 4.1 centimetres long, which represents 4.1 amperes. Now you'll remember in a previous video we spoke about the degree of separation between the three phases that feature in a three-phase system, and you remember that all-important value of 120 degrees. So what I'm going to do now is draw my next arrow at 120 degrees from the first one, down there like that. So there's 120 degrees. And then I'm going to represent what's happening with L2. So here we've got 16.1 amperes. So I'm going to draw a line that is 16.1 centimetres long. As I say, it's not strictly speaking necessary to draw this method to scale, but I'm just doing it A, because I quite enjoy doing it, and B, because it helps us to visualise exactly what's happening with this circuit. So that's our L2 value, and that line is 16.1 centimetres long, which represents 16.1 amperes. And then finally, I'm going to draw at an angle of another 120 degrees from my second line here. So there's my 120 degree mark. So we'll get that penciled in over here. So there's 120 degrees. And I'm now going to draw a line that is 8.1 centimetres long. And if I've done my layout correctly, that should fit on here quite nicely. So we'll go 8.1 centimetres. and that represents 8.1 amperes. So there we go, there's our 8.1 centimetre line. So L3 equals 8.1 amperes. So this is actually what's happening with the currents inside our three-phase system. We've got L1 drawing just over 4 amps, L2 just over 16, and L3 just over 8. Now, in order to figure out what's happening with the neutral, what we need to do is resolve these arrows. Now, let's put this into a slightly different context. Imagine that each of these lines represented a pulling force. So we've got an object in the middle of this drawing here, and it's being pulled in that direction with a force of 4.1 newtons. It's being pulled in this direction with a force of 16.1 newtons, and this direction with 8.1 newtons. What's going to happen to that object? All of those forces are going to kind of resolve themselves, and actually what's probably going to happen is that the object will end up moving kind of slightly off in this direction if they were all pushed on it at the same time. And actually that's exactly what we're going to figure out is happening, because that distance that it would move would actually represent the value of our neutral current in this analogy. So we need to do something now, and it's called, we need to break our currents into their vertical and horizontal components. Now, that might sound a little bit baffling at first, but actually what I'm going to do next will hopefully help us to understand this a little bit better. I'm going to now lay my arrows, my three-phase system, out onto what's basically a coordinate grid, a Cartesian grid. So I'm going to draw my y-axis there, and then I'm going to draw my x-axis coming along here, and draw it along the bottom so I can get it a little bit more accurate there. Okay, so I've created a grid here that illustrates what's going to be happening with our current. So this is our x-axis, this is our y-axis. Obviously we know that along here we've got our values. So you can see that what we've done here is we have laid out our grid system on top of our three-phase arrows. And now what we're going to do is, when we talk about breaking these down into their horizontal and vertical components, all that actually means is we're going to figure out what the coordinates are for the endpoints of these arrows. So in other words, I need to figure out what's the coordinates there, what are the coordinates there, and what are the coordinates there. Now, we could, if we wanted to, we could simply eyeball this up, and we could say, well, that's about 14 on the x-axis and about -8 on the y. But actually, we're going to do this via calculation. And the reason we do it via calculation is it gives us a much more accurate mathematical answer. So what I'm going to do now is just lay out a little table in the bottom left-hand corner here. So the table is going to consist of the three phases, L1, L2, and L3. And then we're going to figure out what are the x and y coordinates of the ends of those three arrows that we've drawn there. Now, L1 is really, really easy to find. If we look along the x-axis and we're trying to find what the x value is of that point there, you can see that it lines up with 0 on the x-axis. So therefore we put a 0 under the x. L1, however, has a vertical value of, obviously it's 4.1, isn't it? Because that line is 4.1 centimetres long, representing 4.1 amperes. So the y value is 4.1. So that's nice and easy. No maths required for that, really. When we start thinking about finding the x and y values for L2, bearing in mind that this is the horizontal component and this is the vertical component of L2, it gets just a little bit trickier. We've got to start thinking about incorporating some trigonometry into our calculation. So what we're going to do first of all is we're going to find out what is the x value of L2. So that's the first thing that we want to do. Now, the way that we do that is we want to think, right, I want to know what point on the x-axis lines up with the end of that arrow. And what I can do is I can actually just draw that in as a dashed line there. Now, when I draw this in as a dashed line, what you realise suddenly is we've got a familiar shape buried inside this image. What we've got here is a right-angled triangle, and we know that we can use trigonometry to solve a right-angled triangle as long as we know the length of one side of the triangle and one angle. Now, if you're not sure about your trigonometry, then please go and watch the video that I made on the trigonometric identities, as it's going to help you to understand this part of the video a little bit better. So let's think about this logically. Let's figure out what we know about this triangle. We know that this length here is 16.1. So that length there is 16.1. And because this is the long side of the right angled triangle, we know that that is the hypotenuse of this angle, of this triangle. So the question we now need to know is, if we know that that's a right angle, then we need to know either this angle or this angle. Well, can we figure it out? Well, surely we can. We know that the angle from here round to here is 120 degrees. We discovered that in a previous video. We also know that this axis and this axis form a 90-degree angle there. So if we do 120 degrees, take away 90 degrees, it leaves us with this angle here. So now we know that this angle is 120 degrees minus 90 degrees, which gives us 30 degrees. So that angle there is 30 degrees. This symbol here is the Greek letter theta, and it's just used in maths to represent an angle. So the angle theta is 30 degrees. Now, because we want to figure out what this point is on the x-axis, we want to know what's the length from here over to here. So we want to know what this side of the triangle is going to be. How long is that going to be? And this side of the triangle will actually be what we call the adjacent, because it is adjacent to the angle. Again, if these terms are unfamiliar to you, please go and watch the video that I've created on the trigonometric identities, because you need to understand that to understand what we're doing here. So from that previous video on the trigonometric identities, we know that the cosine of theta is equal to the adjacent divided by the hypotenuse. So that is the way that we remember the relationships between our angles and sides of a triangle and their trigonometric identities. So what we need to do here, though, is we don't need to know the cosine of theta. We need to know the length of the adjacent. So we need to transpose this formula. So at the minute, we've got that adjacent and we are dividing it by the hypotenuse. The opposite of dividing by the hypotenuse is to multiply by the hypotenuse. So we end up with the adjacent being equal to the hypotenuse multiplied by the cosine of theta. Now, if we perform this calculation, it will give us the length from there to there. So let's put this into our, let's put our numbers in here. So we've got 16.1 times by the cosine of 30. And as we can see from the calculator on the screen now, 16.1 times the cosine of 30 gives us 13.943 plus change. So we'll just say that that is equal to 13.94. And as you can see, actually, if you follow that line up, you can see that it meets the x-axis just behind the 14 mark there. So 13.94 is an accurate representation. So the x value for L2, in other words, the position of that x there, the coordinate of that position there, is 13.94. Now what we've got to do is figure out the length of this side of the triangle, and that will give us our y value, because if we track this from here across to where it meets the y-axis, so if we do something like that, then you can see that it meets the y-axis at just past -8 there. So we're now going to figure out what is the y value of L2. Now, what we're actually finding here is we're finding this side of the triangle, the length from that point down to that point there. And that is the opposite side of this triangle. And we know from our studies into trigonometry that the sine of theta is equal to the opposite over the hypotenuse. So when we change this around, that becomes the opposite is equal to the hypotenuse multiplied by the sine of theta. So when we put the numbers in, we end up with 16.1 times by the sine of 30. Now, if you know a little bit about maths, you'll know that the sine of 30 is exactly 0.5. So when we put this into our calculator, as you can see here, we do 16.1 times by the sine of 30. It'll come out at 8.05. So that comes out at 8.05. Now, one really important thing that we need to bear in mind, when we now put this y value into our table here at 8.05, what we need to bear in mind is that this coordinate here is on the negative part of the y-axis. So actually, we're at minus 8.05, because if we were to map that coordinate at 13.94, 8.05, it would be pointing up in this direction, which is obviously no good to us in this instance. Okay, so now we've done that, we need to do exactly the same thing again for L3. So we need to figure out what the x and y coordinates are of L3. So again, if we want to figure out what the end of this arrow is going to be at on the x-axis, it's going to be somewhere around here. So you can already see our answer should be somewhere around -7. So we'll see what we come out with. So what is the x value of L3 going to be? Well, again, we need to know the angle. We need to know what this angle is here. Fortunately, we know that between here and here is 120 degrees. Between here and here is 90 degrees. So 120 take away 90 leaves us with theta for this angle of 30 degrees once more. So we've got the same angle there, which is super helpful. It's worth noting at this point that this is a purely resistive load that we've got here. Because it was just heating loads, it's pretty much purely resistive, which means that the angles between the currents will be 120 degrees. Where you start incorporating motors and things like that, then it may be that these aren't quite at 120 degrees from each other, but that's the subject of a much future video. Right, so let's figure out what the x value of this triangle is, of the end of this arrow here is. So again, we go back to our original formula. We want to know the length of the adjacent, which is adjacent or next to the angle. We know that the hypotenuse here is 8.1 units long, so that's the hypotenuse there. So let's volley that into our mathematical formula. So cos theta is equal to the adjacent over the hypotenuse. I sometimes get asked the question, how come you can remember all of this stuff, Joe? How do you remember all these formulas and maths and stuff? And the answer is it's because I do it again and again and again and again. Every time I write out a calculation, I always put the formula in, do any transposition, put the numbers in, and then write the answer down. And by doing that, because you repeat the formulas over and over again, they just get lodged in your brain. So that would be my top tip if you want to remember these formulae. Just keep on repeating them, and that will really help you to get them lodged in your brain. Okay then, so rearranging that formula like we did before, we get the adjacent is equal to the hypotenuse times by the cosine of theta. So therefore we've got, in this case, 8.1 multiplied by the cosine of 30. And that means that we end up with, if we just put that into our calculator, 8.1 times by the cosine of 30, we end up with 7.014. So again, we'll round that off to 2 decimal places. 7.01 is what we come out with there. Now bear in mind again, I'll put this into the table, 7.01, but look at where that point is. It is on the negative part of the x-axis, so that is minus 7.01. And then finally, we just need to find the y value of L3. So once again, we're trying to find the distance from the end of the arrow up to here, so we want to know the length of that, so that is the opposite, and we can find that roughly by tracking it across the end of the arrow across to our y-axis. So we know that we're aiming for somewhere around -4, just over that. So again, you don't need to do this to scale. You can do the calculations without drawing this bit to scale, but I always find it's useful to have a sketch of this just to help you see where on the x and y axis you are, and it'll help you not to forget your positives and negatives, which is really, really important, as we're going to find out. So let's put in here now our calculation. We want to find the opposite, so we're dealing with the sine of theta is equal to the opposite over the hypotenuse. Some of you will remember SOHCAHTOA from when you were at school. This is where it starts to come in handy. We then transpose the formula to find the opposite, which is equal to the hypotenuse multiplied by the sine of theta, and therefore is equal to 8.1 times by the sine of 30. And again, we could actually do it without the calculator this time, because we now know that that is just going to be half of 8.1, because the sine of 30 is 0.5, but let's put it into the calculator anyway. 8.1 times the sine of 30 gives us, amazingly, 4.05. So we've got 4.05. So that's the y value of the end of that arrow. So we'll put that into our table, 4.05, bearing in mind, and this is absolutely critical, that that is on the negative part of the y-axis, so that is a negative value. So in this little table here, what we've done is we have broken each one of those currents into their horizontal and vertical components. In other words, we've found out how far they go along the x-axis and how far they go up or down the y-axis. Now what we need to do, because we're interested in the combined effect of these currents, in other words, what happens with these currents when they all meet together inside the neutral conductor, we need to combine these vertical and horizontal components. And all that means is that basically we just add or subtract them depending on whether they've got a negative in front of them. So here we've got 0 plus 13.94, and we're adding that because there's like a little ghost plus in front of the 13.94. And then we're taking away 7.01. So if we do that on our calculator, 13.94, and then we minus 7.01, we end up with 6.93. So we've got 6.93. And what we've found there is the horizontal component of our neutral current, 6.93. So that's going to be somewhere here on our drawing. We then do the same with the y values. So we have 4.1, and then from that we're going to subtract 8.05, and then we're going to subtract 4.05, and that gives us a really nice round number of minus 8. So actually we could plot our neutral current onto this table now. So we've got 6.93, which puts about there on the x-axis, and if we come down to minus 8, which is about there, the end of our neutral current arrow will be about there. So we could actually plot this out, and then we could actually, if we wanted to, just measure the neutral current. However, we're going to calculate it because we can be much more accurate. So this line from here down to the coordinates of that neutral current right there, the length of that arrow represents the amount of the neutral current that we've got in this system. Now, as we say, we could measure that and figure out what the neutral current will be. But what we're going to do is we're going to calculate it first, and then we'll just measure it just to see if it's in the ballpark. So we'll have a little look at this, and we'll think about how we can turn this into a calculation. Now, the good news is that buried inside here, we've got our shape that we love, our triangle. I once had a learner say of me, that guy, all he's interested in is triangles. And it's true, I do talk a lot about triangles during my lessons, but that's because they're very important in electrical science. And they're just a beautiful thing as well. So there was a fair shout. So we've got a triangle buried inside here. We've got this triangle here buried inside our graph. So what we can look at here is we can think we want to figure out how long that line there is. Well, we know how long this dashed line here is. We know that that is 8 units long. And we know that this line here is 6.93 units long. So we know two sides of a right angled triangle. And if we know two sides of a right angled triangle, we can use Pythagoras' theorem to figure out what that's going to be. A squared plus b squared equals c squared. So what we're going to do is we're going to figure out, by putting our numbers in, what the length of this side here, c squared, what the length of c will be. So again, if you're not sure about Pythagoras' theorem, please go and watch the video that I've made on that, because it will help you to understand what we're doing here. Now, we're not interested necessarily in finding c squared by itself, we're interested in finding c. So we need to square root both sides of this formula before we begin. So we have c is equal to the square root of a squared plus b squared. So here we can say that a will be equal to 6.93, b is equal to 8, and c will be equal to the length of this line here. So let's do that now. We'll put our numbers in. We've got the square root of 6.93 squared. Now you'll notice here that I've kind of ignored the fact that this is a negative value down here, because actually it doesn't matter the orientation of this triangle. We're just interested in the lengths of the sides, which is why I'm not worrying about the fact that that is a minus 8 value. So we've got 6.93 squared plus 8 squared and then square rooted. So again, let's put that into our calculators, and you do it in the following way. Hit the square root button, and then we go 6.93 squared, and then we're going to add on to that 8 squared and see what we come out with. So we end up with 10.58. And what we've actually found there is not just the length C of this triangle. What we've actually found out is the calculated neutral current. Now, the sharper eyed among you will immediately notice that what we've got here is not exactly the same as the 10.2 amps that we measured, but actually it's very, very close. We're within 0.38 of an ampere with our calculation. Reasons for that, maybe the measuring equipment, maybe the fact that all of the loads were not perfectly resistive, maybe there's a little element of inductance in the heating element inside the unit. There might be one or two things that have caused this to happen, maybe slightly varying voltages within the system as well. But you can see that the principle is sound. We've got very, very close to our measured neutral current. So you can use this method if you know the loads that are going to be connected to a three-phase board. Then you can use this method to calculate what the neutral current will be flowing out of that distribution board down that submain, which is pretty important and quite useful. And you can do that long before you do any installation work as part of your design work. So let's just kind of prove this point here. So if I measure the length of that line there, you can see it's coming out at about 10.5, which is about what we calculated. And it's very, very close to the 10.2 amps neutral current. So as we say, this is my preferred method of how to perform this calculation. If I was going into an exam, this is the method that I would use. It's long-winded, but I can follow each step very closely and I can see what's happening. You might be looking at this method and thinking that is a very, very complicated way of doing this. Isn't there an easier way? The good news is there is some easier ways, and we're going to show you those in future videos. However, it's quite important that when you're in your exam, that you read the question paper very, very carefully, and if it asks you to use a specific method, you must use that method, otherwise you will lose points for that question. If there is no specific method that is stated, then obviously use whichever one you're most comfortable with, but it's always a good idea to check with your teacher before going into the exam if there is a preferred method that that examining board prefers for you to use. So that's how we calculate neutral current inside an imbalanced three-phase load, remembering that an imbalanced load is one where all the currents are different. And in future videos in this series, I'll be showing you other methods of how to calculate that neutral current using the same values that we got on our original experiment. So thank you very much for watching.